In this lecture, we apply second-order Runge Kutta methods for finding approximate solutions to an initial value problem. The initial value problem is given by the differential equation y prime equals e raised to the power minus t squared times y, with y of 0 equal to 1. We define f of t y to be equal to e raised to the power minus t squared times y. With the help of the software Mathematica, we are going to find approximate solutions to this initial value problem on the interval from t equals 0 to t equals 1.5. Here is the general recursion formula for the second-order Runge Kutta method. In this formula, y sub k is the approximation if not the exact value of y of t sub k. H represents the step size between the partition points t sub k of the interval from t equals 0 to t equals 1.5. If we apply a uniform partition to the interval using the partition points t sub 0 all the way up to t sub n, then the step size h will be equal to t sub n minus t sub 0 divided by n. T sub n will be 1.5, and t sub 0 will be 0, so that h will be 1.5 over n. T sub k plus 1 will be t sub k plus h. The second-order Runge Kutta methods that we will apply here are the midpoint method and the modified or improved Euler method. The modified Euler method is also often referred to as Heun's method. For the midpoint method, alpha equals 0, beta equals 1, and both r and s are equal to 1/2. And for the modified Euler method, alpha and beta are this time both equal to 1/2, while r and s are both equal to 1. This part of the modified Euler method is the preliminary predicted value for y sub k plus 1. We call it yp. And so we write the recursion for the modified Euler method in the following way. We will also fit a differentiable curve to the discrete points forming the approximate solution generated by each method. To keep it simple for this exercise, we will use the Lagrange polynomial passing through all the points as the differentiable curve for each method. Then we will check graphically how well the Lagrange polynomial satisfies the differential equation. So let's start the Mathematica code for the midpoint method. We first define f of ty. F of ty is e raised to the power minus t squared times y. T sub 0 is 0. Y sub 0 is 1. For the initial run of the Mathematica code, we set n equal to 10. H is 1.5 over n. We apply a do loop for the recursion. Inside the do loop, we have a set of commands starting with t sub k plus 1 being equal to t sub k plus h. Then it's the recursion for the y sub k's. We have y sub k plus 1 equals y sub k plus h times f applied to t sub k plus 0.5 times h, and at y sub k plus 0.5 times h times f of t sub k, y sub k. K goes from 0 to n minus 1. We call the set of points of the approximate solution points, and we use the table command. Inside the table command, we have the pair of coordinates t sub k and y sub k. K goes from 0 to n. We execute the entire code to see on screen the coordinates of the points of the approximate solution. We suppress the on-screen output of these coordinates by typing a semicolon at the end of the points command, and re-execute the entire code. We now plot these points. We store the plot of the points in the variable plot10. We list plot points. We color the points red, so we apply the plot style option with the RGB color directive. We have 1 for red, 0 for green, and 0 for blue. We also specify the range of the y values. To ensure that all the points will be shown on the graph, we specify the plot range for the y values to be between 0 and 2. We execute the code, and we have the plot of the approximate solution. For comparison, let us increase n from n equals 10 to n equals 100. We call the new plot plot 100. This time we color the points blue, so it's 0 for red, 0 for green, and 1 for blue. We will initially suppress the on-screen plot for n equals 100 by typing a semicolon at the end of this line of code. We wish to combine the plots for n equals 100 and for n equals 10, so we use the show command. We show plot 100 first, followed by plot 10. This way, plot 10 with its fewer points will be superimposed over plot 100. We evaluate all the lines of code. And here are the combined plots. The points of plot 10 seem to be close to lying if they don't already lie on the curve that would contain the points of plot 100. This seems to imply that the points for the approximate solutions for n equals 10 and for n equals 100 generated by the midpoint method are close to the corresponding points on the exact solution. We can try fitting a differentiable function through the points of either approximate solution and see how well this function satisfies the differential equation. For this curve-fitting exercise, we will use the Lagrange polynomial passing through all the points for n equals 10. This time, we will no longer require the list plot and the show commands for the next phase of this exercise. We call the Lagrange polynomial g of t. We apply the interpolating polynomial command. It's the interpolating polynomial for points using the variable t. Executing all the command lines, we get to see the Lagrange polynomial through all the points of the midpoint method approximate solution. Now, to see how well g satisfies the differential equation, we plot the difference between g prime of t and f applied to t and y, where y is replaced by g of t. We first type a semicolon at the end of the definition of g of t and execute the code again to hide g of t. We plot g prime of t minus f applied to t and g of t. T goes from 0 to 1.5. We will color the curve red. So we have for RGB color 1 for red, 0 for green, and 0 for blue. Hoping that this difference is close to 0 if not equal to 0. Let's specify a plot range from -1 to 1. And we execute all the lines of code. From this plot, with the curve of the Lagrange polynomial lying very close if not on the t-axis, it looks like that the polynomial does a decent job satisfying the differential equation. Let's zoom in by changing the plot range so that y lies between -0.01 and 0.01, and execute the entire code. From the graph, it seems like the absolute error of g in satisfying the differential equation, that is the maximum value of the absolute value of g prime minus f of t g of t, seems to be less than 0.003. Now let's try this out this time with the modified Euler method. In the recursion for the modified Euler method, we first need to define yp. Yp equals y sub k plus h times f of t sub k y sub k. Then it's the formula for y sub k plus 1. Y sub k plus 1 is y sub k plus 0.5 times h times the sum of f of t sub k y sub k and f applied to t sub k plus 1 yp. We execute all the lines of code. The largest value of the absolute value of g prime minus f of t g of t seems to be bigger than 0.005, which is greater than that for the Lagrange polynomial from the midpoint method, so that it seems that the midpoint method does a better job satisfying the differential equation for n equals 10. A word of caution regarding the use of Lagrange polynomials. Sometimes Lagrange polynomials with large degrees will produce oscillations with frequencies and amplitudes that increase with the degree of the polynomial, so that increasing the value of n, or the number of subintervals, may not necessarily result in better approximations. These oscillations are called Runge's phenomenon. This is the plot of the absolute value of g prime of t minus f of t g of t for n equals 100 for the modified Euler method. Runge's phenomenon is quite evident near the endpoints. Because Runge's phenomenon can be attributed to the degree of the Lagrange polynomial, one can instead use, for example, cubic splines, whose degree, as the name suggests, is no more than 3 in the hope of avoiding Runge's phenomenon.